Hello, welcome to the first episode of Physics from Scratch, a physics channel where we learn physics from the ground up, one episode at a time. We're going to go on a big journey, understanding new physics principles episode by episode, and we'll do it in a way that you can actually understand without being buried in formulas or theories. With that out of the way, let's jump right into the episode. Here's a thought experiment. If the world got hit by some catastrophe that destroyed all of our scientific knowledge, what would be the one sentence you would give to future generations that had the most information in the least amount of words? Famous physicist Richard Feynman's answer is the atomic hypothesis. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. Have you ever noticed that ice, water, and steam are all the exact same thing, just water, and yet they look and behave completely differently? Ice is hard, water flows, and steam disappears into the air entirely. So what's actually different between them? To answer that, we need to look a lot closer than we normally would. Imagine a drop of water on the table. At first, it may seem extremely straightforward, but that's because we aren't looking at it from the right perspective. Right now, we are looking at it from a macroscopic point of view, meaning we are looking at it from a size we can see and feel. Now, let's zoom in a billion times. We are now looking at it from a microscopic point of view. We are at a size where we can't see or feel. So, what are we looking at? Well, there are a lot of identical objects clumped together. We can see that these objects are composed of one big orange circle accompanied with two small white circles attached to the big one. Each of these circles is an atom, and each cluster is a group of atoms forming what is called a molecule. The white circles are hydrogen atoms, and the orange circles are oxygen atoms. This figure is extremely simplified. First, the particles are drawn very simplistically with clean borders, which is inaccurate. Second, this is drawn in two dimensions, when in reality the molecules are all moving in three dimensions. Atoms are always in perpetual motion, dancing, bouncing around, and turning around each other. You should think of this as a dynamic process instead of a static one. Atoms are always stuck together, as they attract each other, but if you try to push them together, they will repel each other. This mutual attraction is also why everything around us stays stable and holds its shape. It's what's holding molecules together. Atoms have a radius of 1 or 2 times 10 to the negative 10 meters. To simplify measuring atoms, physicists use a unit of length called an angstrom, named after Anders Angstrom, which is zero point 0.1 nanometers. So atoms have a radius of 1 or 2 angstroms. If you line atoms one by one, it would take you 1 million atoms just to recreate a strand of hair. So we know atoms are tiny, and we know they're constantly moving and pulling on each other. Here's something you've probably noticed but never thought to ask. Water evaporates faster on a hot day than a cold one. Why would temperature have anything to do with that? This is because atoms' constant motion is called heat. When we increase temperature, we increase atoms' motion. If we heat water, the atom's motion increases, and so does the space between them. If we keep on heating, there comes a point where the atomic attraction is too weak and the atoms disperse. The water we started with has now become vapor. In reality, at a normal atmospheric pressure, there are relatively few water molecules in a room, certainly not three in a rectangle this size. We'd normally see none or maybe one. In vapor's case, we can clearly distinguish the singular molecules compared to water. The atoms here are also drawn 120 degrees apart for simplicity, but the real angle for water molecules is 104.5 degrees, and the distance between the center of a hydrogen and the center of an oxygen is 0.957 angstroms. Let's observe some of vapor's properties. Just like atoms in a liquid, gas molecules are in perpetual motion, constantly bouncing off everything around them, including the walls of whatever container they're in. Imagine you're making popcorn in a sealed pot. Each kernel flies around and slams into the lid randomly, and on its own, any single hit means nothing. But with enough kernels colliding non-stop, all those tiny impacts add up to a steady push you can actually feel if you try to hold the lid down. That steady push is pressure, the combined force of countless molecules colliding against the surface, all at once, all the time. Here's a container of gas sealed by a piston. The exact shape of the molecules doesn't matter much here, so we'll simplify them as little circles with arrows showing their motion. These molecules are moving in every direction, constantly, and a huge number of them are slamming into the piston at any given moment. All of those collisions together are what push against the piston. That combined push is the gas's pressure. Now, let's put twice as many molecules as before, keeping them at the same average speed, meaning the same temperature. This doubles the number of collisions, and so doubles the pressure. So we can deduce that pressure is proportional to density. But there are two complications. First, atoms attract each other, and right as a molecule is about to hit the wall, its neighbors are still pulling it backward. That little tug slows it down just before impact, so it hits a bit softer than expected, which makes the real pressure end up a bit lower than this simple picture predicts. Second, atoms aren't actually points, they take up real space. So the room molecules have to move around in isn't the full container. It's the container minus the space already taken up by every other molecule. That extra crowding makes them bump into the walls more often than expected, which pushes the pressure a bit higher than the simple prediction. Neither of these complications is significant when the gas is sparse. Both shrink toward nothing as density gets low. So at low density, pressure ends up proportional to density, just like we said. Now what if instead of increasing the density of the gas, we increase the temperature? As mentioned before, heat is atomic motion, so we would be increasing the atom's speed. Since the atoms are faster, they collide more often, meaning pressure is also proportional to temperature. Finally, let's imagine another situation. Let's imagine the piston is now slowly being pushed inward so that the atoms are being compressed. This means that when atoms collide with the piston, they're going to bounce back with more speed, so more heat than before. You can test this out by playing ping pong. If you hit a ball coming your way by moving your racket into the ball, it's going to go back faster. This means that every atom will be faster and by inference hotter. So when we compress the atoms in a gas, the gas will get hotter, and if we decompress, the gas will get colder. Fun fact, the density and attraction effects we covered earlier are actually the basis of something called the van der Waals equation, which physicists use to describe real gases more accurately than the simple version we just covered. Now that we know a lot about heating atoms, let's go in a different direction. Instead of increasing temperature, let's see what happens when we decrease it. We know that heating can break the atomic attractive force, so cooling can strengthen it since the attraction has less movement to account for. Once we cool water to low temperature, we get this. The water molecules have now formed into a rigid structure called ice. What stands out is that each atom has its own place. If you know how the atoms are arranged at one end, you can predict the arrangement at the other end, because the same pattern repeats throughout. So if we push the atoms with a microscopic needle, the atoms would stay rigid as opposed to the liquid form, where upon contact, each atom would go in a different direction and the structure would be unstable. The difference between liquids and solids is that the atoms in a solid are held in something called a crystal lattice. The position of one atom is determined by the position of another, and vice versa. This drawing is an imaginary portrayal of ice, and while it has some aspects correct, it is still inaccurate. One of the correct aspects is that ice has a symmetrical hexagonal structure. Rotate the drawing 60 degrees and it looks exactly the same. If you're observant, you'll notice that this is why ice flakes have a hexagonal appearance. The drawing also shows us why ice loses volume when it melts. You can see numerous holes in the structure that can be occupied by other molecules. This open lattice structure also explains something you've probably noticed without thinking about it. Ice floats. Most substances get denser when they freeze. The atoms pack tighter as a solid. Water does the opposite. The hexagonal structure takes up more room than the liquid, so ice is actually less dense than water. Water isn't even completely alone in this. A handful of other substances like bismuth, gallium, and silicon do something similar. Although ice has a rigid structure, its temperature can still change. Ice still contains heat like every other state. But what is heat in the case of ice? Well, the atoms are still constantly moving, which means that even though each atom has an ordered place, they still vibrate on the spot. When we increase the temperature, the vibrations become more and more important until each atom is ejected from its spot, transforming the ice back into water. This process is called melting. When we decrease the temperature, the atoms vibrate slower and slower until at absolute zero, which is minus 273 degrees Celsius, the atoms hit their minimum motion, which is not zero, but still the minimum. This minimum amount of motion is not enough to keep most substances from freezing solid, with one exception: helium. Even at absolute zero, helium retains just enough motion to stay liquid, unless we increase the pressure enough to compress the atoms together and force it to solidify. Before we finish this video, I'd like to ask you a question to further get you thinking. This is going to be a tradition every episode, a scratch question to leave you with something to chew on after the lesson is over. Today's is about the states of matter we covered. We talked about solid, liquid, and gas. All of them are just water atoms behaving differently depending on how much they're moving. So here's something to think about. Is it possible to imagine another state of matter beyond these three? I'll give you the answer next episode. And that's it for this episode. We saw how atoms simply moving and pulling on each other explains why water turns into vapor, why gases push back when you compress them, and why ice floats instead of sinking. Next episode, we're going to look at what happens when atoms don't just move around each other, but actually combine and rearrange. If you want to keep learning physics from scratch, consider subscribing, as these videos take a long time to make. See you next time.